Lesson 39, area, which sounds like a really, really basic concept, right?
Yeah.
What shape is this?
That is a
Supposed to be
A
rectangle. Pretend I drew that straight.
It's a rectangle.
It's a rectangle. How do we find the area of a rectangle?
The width times length.
Okay. Which one do you want to be with? What do you want this one to be?
Width.
Width. Okay. And this one, so this will be length.
Yeah.
Alright, so we do length times width. Pretty basic, right?
Yep.
Well, that's all fine and good. What if we have a shape like this? Oh, and so these are all straight lines with right angles here, right? What if we have a straight line and a right angle with a straight line and a right angle with a straight line and then something that isn't a straight line? They want to find the area of this thing.
You pull out your magical machine and tell it to do it for you.
You give it to Luke.
You get what?
You give it to Luke.
Okay. Here, math this for me. The idea is, let's say if we have drawn on our axes, on our graph here, something, let's say that this curve is part of the equation. Actually, that looks more like it should be what? Plus 2, plus 3? Let's call it 3. So this is one of the main ideas that calculus is about. Like the two main ideas are derivatives, which we've covered quite a fair bit, and integrals, which we started doing a little bit of. One of the main ways that integrals are used is to do something like this: is to find what's called the area under a curve. So if we have some kind of a curve defined by an equation, and we define a left and a right bound with some kind of interval, from x of this to x of this. And so between those two x values and down from the x-axis up to whatever the curve is. That's one of the things that integrals are used for. And so what we're going to do to try to start solving it, the book kind of does it in about 3 pieces. Just to break you in to the idea, is what we're going to do. What if I took this shape and I tried to approximate the area, get as close as I can, by using a rectangle? Because we know how to do a rectangle. Yay, rectangles.
Yeah.
If I took this shape, and let's say that if I took the bottom end of this here, and I made a rectangle like this. Right, so same width, and then using that dotted line as the top end, I could whatever this number is times whatever this number is, and that would give me the area here. And I would know that would be kind of close to what the value of what the area of that shape actually is, but it would be on the low side, right? Because it does not take into account this little piece up here. You with me so far?
Yep.
Now let's say that I wanted to make another estimate, and instead of a conservatively low estimate based on the lower end of this curve, what if I wanted to take it onto the higher end? I just took the top here, and I went across there, and so I did a rectangle like this. That would also be an approximation of the area of that rectangle, but it would be on the high end, right? We would know that it's kind of close, but it's more than the actual area because there's this extra space up here that's not part of the actual shape that we're looking for that is included in this area. So in a general sense, what we call these, this idea would be a lower bound or lower, what's the word I'm looking for? Well, I can't call it a sum yet, without doing. This would be a lower estimate, this would be a higher estimate, and we know that the area is in between, like the actual area is in between whatever these two numbers are. With me so far? Right?
Yeah.
Let's take that same idea And what if, instead of making one rectangle out of that, let's split it into two rectangles. So we're going to take that same idea, and we're going to try to get a little bit closer to it. Are they using pink or red?
Red.
Red? What if I took this interval here and I cut it into two pieces? And then I took the lower end here, made a rectangle, and then on this one I took the lower end and made a rectangle. That would be closer to the actual area than if I just used one rectangle, right? I'm still low because I'm missing this piece and that piece, but I'm including this much here, this area here that I wasn't before. So I'm closer. Right. By the same token, if I wanted to do an upper estimate, I could take, instead of going to the high end and going all the way across, I went to the high end and I just came over to halfway, and then this half I did the higher end. I would still know that the area of those two rectangles is more than the area that I'm looking for, but it's closer, because now I would not be including this area here. Alright, let's take that same idea, and what if I did it into four rectangles now? You know, these are right angles. What if I did it in four rectangles now? I could do a lower one here, and 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 I could add up those areas. And I know that I'm still low, but I'm even closer than I was before. Just like if I did upper ones, and I only went to here, and an upper one here, and an upper one here, and an upper one here, I know I'm still higher than the actual area, but I'm closer. So the more rectangles that we have, the less room for error there, the less error margin that there is. So what we're going to do is we're going to get some practice in calculating these areas based on a curve that's defined. We're going to pick a certain number of rectangles, equal width rectangles, and we're going to find the areas of all those rectangles and add them all up. Sounds like fun.
Yeah.
Except not really. Yeah. Do you have any trouble understanding this concept? No. As with many things, this is one of those things where the concept is simple, but it's a lot of work. And this is why I gave you several days for this lesson.
Thanks, calculus.
Yeah. All right. So what we're going to do, just so that I'm following the example of the book now. The drawing seems a little skewed, but the drawing in the book is using x squared plus 1. So just pretend that this is only y. And let's walk through a couple of these. So on our, following their example, this would be at 0. This would be 1, and this would be 2. So we have 0, 0.5, 1, 1.5, 2. Describe to me the coordinates of this point right here. What are those coordinates?
1.
Okay, so this dot here is 0, 1. This dot here is 1, 2. And this dot here is 2, 5.
Yes.
Okay. Alright, so if I draw a rectangle here, and a rectangle here, and a rectangle here, and all I'm doing here is I'm taking the, since I've divided this into 4 rectangles, for each rectangle, the tops, the 2 sides go to different heights. I'm taking the lower one and cutting it off there and making a rectangle. That's what we do for a lower sum. All right. So, okay. So what's this right? What's the coordinates of right here?
0.5, 1.25.
Okay. And what's this coordinate right here?
1.5, 3.25.
Okay. So what are we going to do then? What's the area of this rectangle? What times what?
0.5 times
1.
Okay.
Point-
0.5
yeah,
times 1. What's the area of this rectangle?
0.5 times 1.25.
Right. Okay, so this one is 0.5 times 1. This one is 0.5 times 1.25. This one is 0.5. So all these are going to have the same width, 0.5, right?
Yep.
Okay. So this one is 0.5 times 2. And this one is 0.5 times
3.25.
Yeah, that's right.
And so if we add all these up, we are going to get what's called a lower sum. And by the way,
Let's grab this.
Wait,
Scale.
is there?
and notice it's 0.5 times this, 0.5 times this, plus 0.5 times this, plus 0.5 times this. I can factor out 0.5 from all that, right?
Yes, you can.
So I'm going to have 1 plus 1.25 plus 2 plus 3.25.
That's pretty.
Pretty neat.
That's pretty neat.
And how did we get this 1?
It was there.
How did we get this 1?
In the beginning was the y coordinate.
In the beginning was the origin.
Okay.
How did you calculate? One of you guys said that this was 1, that the y coordinate here was 1. How did you get that answer of 1?
Because the y intercepts.
And how did you find what the y intercept was?
Because we found k.
Let me remind you, refer you back to this. How did you find the y intercept?
We took the f of 0.
Yes, you did. So this here, this is the f of 0. How did we get 1.25?
We took the f of 0.5, yo.
Okay, and we got the 2 by doing
The same.
f of
2. Or 1.
1. And this one is the f of
1.5.
5. So we're going from 0 to 0.5 to 1 to 1.5. So we are we're going 0.5. We're moving that far over, and our y coordinate, our y coordinate is the f of the left end of our rectangle, and that's the height of our rectangle. Okay. Let's do an upper sum, which is the same idea, except we're going to be making our rectangles like this. You know, the upper end of things. Alright, so for the upper sum, what's the upper sum? What's the width of each rectangle?
0.5.
0.5. So we know it's 0.5 times something or other, plus 0.5 times something or other, plus 0.5 times something or other, plus 0.5 times something or other.
Yeah, we do.
All right, let's so on the far right triangle or rectangle here, what's the height? 5, which we got by doing
The F of 2.
the F2. What's the height of this one here?
3.25.
3.25, which we got by doing the F of
1.5.
1.5. What's the height of this one? 2, which we got by doing
F of 1.
F of 1. Height of this one,
1.25.
which we got by doing the F of
0.5.
0.5. So we're, and again, since we've got I can factor out the 0.5 and add up all the heights. Oops. Okay. So this here is called an upper sum. This is called a lower sum. And you base it, you get these by doing triangles that way. So on this one here, for the lower sum, we're doing the F of 0, 0.51 and 1.5. For the upper sum, we're doing the F's of 0.51, 1.5, and 2. So they're very, very, very similar, except that the lower sum uses the left one and not the right end. The upper sum uses the right one, but not the left end. Hopefully that will help with the concept. Oh. We still have. I thought class was almost over. Yay. So that's the idea of an upper sum and a lower sum. Well, what's that going to look like? What's that going to look like? This is all fine and good for, notice we have I did it with the area under a parabola where the parabola is only increasing. What if I had a parabola and I want it from here to here? Let's say I want to go from -2 to 2.
Can you just take the guess sum of one side and double it?
In this case, yes.
Oh.
But what if my parabola was shifted over a unit?
And you just have
Okay.
to do the whole thing.
Alright.
Well, the
So
concept's not hard.
where our curve is increasing, a lower sum is would be like this, right? Just like we did over here. Right, we go to the left end because that's the lower end. Draw a line across and do a rectangle there. For this interval here, left end is the lower end. But over here, where the function is decreasing, the lower is at the right end of things. And here, the lower one is at the right end of things. And the same thing with the upper. In reverse, this one, just like over here, this one, an upper sum would be here and here, by measuring the height of the rectangle at the right end where it's higher. But over here, it's the left end that's higher. So if we wanted an upper sum, we'd have to do it from the left end. So notice the adjectives that I've used to qualify what type of sum we're looking for. We have an upper sum and a lower sum. So that when we divide it into rectangles, the upper sum, wherever the rectangle is higher, you go across there, and that's your height. A lower sum is whichever end is lower, and you go across there and get the height. And we can also think of it as a left sum and a right sum. In this case here, because the function is increasing across the whole interval, a left sum and a lower sum are the same thing. Just like a right sum and an upper sum are the same thing. In a case like this, though,
Wouldn't doing in a case where there's both increasing and decreasing, doing a left sum or a right sum would give you a more precise number than either a upper sum or a lower sum?
Well, that's one of the things that you get to think about with these.
We get to think about that.
Because depending on what the curve looks like, you know, there's one type of sum might give you a better estimate than another one. Let me get a couple of different colors. Let's do. Let's say we did, if we did a right sum. If we did a right sum, we would be above here and above here, but below here and below here. So this would be, if I did a right sum, I would be overshooting here and I would be under on this side, which might be what I'm looking for. If I did a left sum, well then I'd be here and here, but I would be here and here. But I'm still dividing, so I'm still taking the curve, dividing the interval into a certain number of rectangles, a certain number of equal width rectangles, and whatever that equal width, whatever that number is, the width of each rectangle is going to be the same, and the only thing that's changing is the height of the rectangle and how I find it. And so in all of these, we will be able to factor out the equal width of the rectangle to make the math a little bit easier. So we're going to, if we have this curve here, y equals x squared plus 2, on the interval from 1 to 3, we want to divide it into 4 equal width rectangles and find a lower sum to approximate the area. It's always good to have an idea of what things look like. So let's see, if we have y equals x squared plus 2, that's a basic parabola shifted up 2 units. So it's going to look about like this. And we want to go on the interval from 1 to 3. So 1 to 3. So we are looking for this area in here. From 1 to 3, from the x-axis to the curve here. And it wants 4 rectangles. So we're going to need 4 rectangles. And we're looking for a lower sum. So we want this. We want this area, this area, this area, and this area. All right. Now, what is the width of our rectangles?
0.5.
Okay. Now, how did we get 0.5?
Because
3 minus 1 and divide by 4.
Hold that thought. What were you saying?
It's 34.
2 divided by
4.
2 divided by 4.
All right. Now, say what you said again.
3 minus 1 first.
Okay. The interval that we're on the interval from 1 to 3. So if we take our y2 minus y1, that will give us this distance. And we're dividing it into 4, or actually, I'm sorry, it's x2 minus x1. And we divide that into, we take that distance and divide it into 4 equal pieces. So I could write this as x2 minus x1 divided by the number of rectangles. And if I'm going to call that delta x. That's my change in x from one side of the rectangle to the next. So my delta x is going to be 0.5. 3 minus 1 is 2, 2 divided by 4 is 0.5, and so that's our delta x. So the lower sum that we're looking for, is going to be, we're going to have 4 rectangles, right? 4 rectangles, each with a width of 0.5. And what about the height? The height of this rectangle is our function evaluated at the left end of it, because that's where the lower end is. So what is the f of 1? Plug in 1 back. Alright. Now the next rectangle, we're measuring at the left end, so we want the f of 1.5. Alright, let me do it this way. That would be 3 halves.
More of this just clicked in my head.
9/4, or 2.25 plus 2.
So 9/4
25.
plus 2.
70/4.
What is this one decimal or? I did it in decimal. Alright, you did it in decimal. Alright, so
4.25.
4.25. Now our third rectangle, the height is at the left end of this, and that's at 2. So what's the f of 2?
6.
And our fourth rectangle, the height is at the left end, so what's the f of 2.5?
8.25.
What, 8.25? Yeah.
C.
Right. And for reasons that we'll get into later, what I want your next step to be is factor out the 0.5s, and then factor out the delta x, and then add up all the heights. So you got 3 plus 4.25 plus 6 plus 8.25, and then multiply that by 0.5, and that will give you the lower sum, which hopefully should be 10.75.
Yep.
Right. 39.2, and that's the answer that we're looking for. 39.2, we want an upper sum. Now that we've been through it once, we can do it a little bit faster. We have a negative x squared plus 9. So we have our parabola opening down, shifted up, and on the interval from 1 to 2. So it's going to be something like this on the interval from 1 to 2.
Yep.
And we want to divide that into 5 rectangles.
C.
So, all right, so 5 rectangles. And we want an upper sum. So upper sum, upper, 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 upper. And what's my delta x? X2.
0.2.
X2
0.2.
minus x1 divided by n.
Yep.
So the length of our interval, which is the distance between here, divided by the number of rectangles that we want. And so what does that come out to?
0.2.
0.2. So our upper sum is going to be our delta, the width of each rectangle, delta x of 0.2. And for the interest of time, I'm going to go straight to this step. Upper sum is at the left end of things. So we want what's the height here?
8.
Here, let me show you like this. The first rectangle has a height of the f of 1. Second rectangle has a height of the f of 1 plus a delta x. That's going to be 1.2.
Yep.
Third one has a height of f of 1 plus 2 delta x's.
Yep.
That'll be 1.4. The next rectangle has a height of the f of another delta x after that,
Yep.
and then another delta x after that.
Yep. Ooh.
So you find the f of 1, the f of 1.2, the f of 1.4, the f of 1.6, the f of 1.8, and you add those up, multiply by the 0.2, and that will give you your upper sum. So once you get the concept and muddle your way through one example, the next example is a little bit easier. Let's set this one up. Y equals negative x squared plus 2x, and we want a lower sum. So we're looking for something that's going to go about like this, from the interval from 0 to 2, and it wants a lower sum. This one is probably going to need a better graph, actually. We're going to need a better graph.
Is this system?
This one looks like from
Yeah.
0 to 2.
And what is the center?
And 1 is the center here, which is also the peak. What's my delta x? Or how do I find my delta x?
Your delta x is 1/3.
Yeah, work with me here. X2
Okay, yeah,
Minus x1
minus 0,
over n.
6,
Okay, so that equals
1/3.
1/3. All right, so my lower sum here is going to be my delta x times the f, let's see, 6 rectangles. Now we want the lower sum. On the left side here, where the function is increasing, the lower sum is going to be at the left end of things. So on the left side here, we've got the f of 0, the f of 1/3, and the f of 2/3. And plus. And on the right side, since the curve is going down, the lower sum is going to be at the right end of things. So we got this one, and this one. So you have to kind of think through. You do want a picture of the graph, even if it's a kind of a sketch, but you do want a picture of the graph. Make sure you're doing it right. Then over here, because we're not going to do the f of 1. Our next one is going to be the f of 1 and 1/3. So 4/3. The next one is the f of 5/3.